Okay, these are the notes that we did last week on quadrilaterals. I'm going to go through and do all the properties of parallelograms, squares, rectangles, rhombi, and then trapezoid and kites will be the conclusion part. We went through everything except trapezoids and kites in class, so a lot of the first of this will be a review. So if you want to fast forward through this, or if you want to double speed it, you can. That way you can kind of still get the notes and still remember what they are as you do the assignment. And then you can slow it down or just fast forward to the trapezoid and kites part, this part that we missed in class. You can pause, rewind, whichever parts that you feel like you need to review to help you with the assignment that's due on Monday. So starting with parallelograms, we have our definition. These are the notes that we took last week. Opposite sides are going to be parallel. That's the first property. And if you're given that it is a parallelogram, so notice that given information here, we have that picture. It means that the opposite sides are parallel. So LE and AK and LA and EK are parallel here. And I marked that with those arrows on the matching sides. And then the reason we can conclude that is because of the definition. If we are given that we have those opposite sides parallel, then we can conclude that it's a parallelogram. So these are kind of the reverses of each other. So here we're starting knowing it's a parallelogram. Here we're starting knowing that we have opposite sides parallel. And again, because of the definition. Now before we get into the rest of the properties, we have some terminology. Opposite sides, sides that are across the figure from one another. You have the pairs of sides here for this parallelogram. Opposite angles are across the figure from one another, so they don't touch. They're not next to each other. But then we have also consecutive angles. So that word consecutive means in order. So S and W are consecutive. W is also consecutive to O. O is also consecutive to N, and N is consecutive to S. So we have all of those pairs, and you have that information on that slide. Okay, as we started to go through those properties, the first one for parallelograms was that opposite sides were parallel. So if we know it's a parallelogram, we know those opposite sides are congruent. We have MI and KL that are opposite and congruent, and then MK and IL. And the reason is because of the property of that parallelogram. Next, the opposite angles are going to be congruent. So S is going to be congruent to O, T is going to be congruent to P. That means they're going to have equal measure. So if we're solving a problem with those, you would set those equal to each other. S would be equal to O, P would be equal to T. The next property has to do with consecutive angles. Now, as a reminder, remember when we did parallel lines and transversals, we had sets of angles that were either supplementary or congruent. Well, we had a pair like this where they're on the same side of the transversal and inside the lines. Those were called same side interior, and those were supplementary angles, which meant they add to 180. Well, we have that in the parallelogram too. These opposite sides are parallel, and so ES acts as that transversal to make these two angles supplementary. So any pair of consecutive angles are automatically going to add to 180. And that's just the next property of parallelograms. You need to understand what a diagonal is. It connects two non-consecutive vertices. Non-consecutive means that they are not in order. Notice in the triangle that none of the vertices are not next to it. Like this vertex is directly next to that one and directly next to that one. So there's not a non-consecutive vertex that we could connect that to. That's why we say the triangle has 0. Here we have 2 diagonals in the quadrilateral. Pentagon has 5. And I kind of have a challenge question for you guys if you want to look at this further. How many would a hexagon possibly have? And then if you could find a pattern between the number of vertices and the number of diagonals, it's really cool to be able to see the connection between properties of vertices and diagonals in figures, and there actually is an algebraic algorithm that you can come up with. So if you guys want to research that further, it's actually really neat. The next property of parallelograms, it has to do with the diagonals. One diagonal cuts it into two congruent triangles. We could also do the other diagonal, and it would also be two congruent triangles, but they would be separate. We have the opposite sides congruent. We know that from the other properties of parallelograms, and also opposite angles that are congruent. So by SAS, or side angle side congruence, we know that those two triangles that we've created are the same triangle, or congruent triangles. We also could have proved it with SAS congruence. It would have taken a few more steps, and we could have done AAS or any of those other triangle congruence theorems. The last theorem, the last property has to do with diagonals as well. When we when we intersect those diagonals, they actually bisect one another, which means they cut each other in half. So that means that this point in the middle is the midpoint of each one of those diagonals. So MA and AO are going to be equal, and PA and AN are going to be equal, and that's what we concluded over here. And it's because the diagonals cut each other in half. The compiled list of properties for the parallelograms: we have opposite sides are congruent and parallel, opposite angles are congruent, consecutive angles are supplementary, diagonals form two congruent triangles, and then the diagonals bisect each other. And the important thing about these properties is they're going to be used to solve problems. So we're going to use these to solve some stuff. So as we go through some of the examples, we're using these sentences and these statements to show how we can find those measures. Like, for example, in this one, in this parallelogram, we're given that we know that that's true. So we know all those 6 properties are true for this figure. So if we're given that 55-degree angle, we know that the opposite angle is also 55. We also know that angle M and H, or M and A, are consecutive, so we know they add to 180. So 180 minus 55 gives me 125. Could have done it with these two as well. And then opposite angles are congruent, so 125 and 125. And then these two are a linear pair, which means they add up to 180. So 180 minus 125 is also 55. You could have gotten this angle Z by noticing that these lines right here are parallel because it's a parallelogram, which makes this a transversal, so those are alternate interior angles. Also, because these lines are parallel, we have this set and this transversal, which makes angle H and angle Z corresponding angles. So we have all those properties from previous material that we've talked about before. Now, the next problem is where we're solving for a variable using the properties of parallelograms. So noticing here, the expressions that have A in them, they represent opposite sides in that parallelogram. So because they're opposite sides, they're parallel and they're congruent. But we know if they're congruent, that means their measures are equal. So I set 6A plus 10 equal to 8A minus 4. And then solving for A using algebra, we get that A equals 7. So subtracting 6A from both sides, then adding 4 to both sides, and 2A equals 14. Dividing by 2 gives me A equals 7. Now, we need to solve for B as well. B, the expressions that have B in them are representing angles here, and angle W and angle Z are consecutive angles. And we know the property of parallelogram says that consecutive angles are going to be supplementary. So we have the measure of angle W plus the measure of angle Z equals 180. So we're plugging in those expressions for each one of those angles. 18B minus 11 was angle W, and 9B plus 2 was angle Z, so we just plug those in. Now we combine like terms. 18B plus 9B is 27B. Negative 11 plus 2 is negative 9 equals 180. combine your constants by adding 9 to both sides, and then dividing by 27, we get that b equals 7. The way to check your work on this problem would be to plug in a for each, or for 7 for each a and for 7 for each b, and see what we come up with. So if I did that, 6 times 7 is 42, 42 plus 10 is 52. So I know side WX now measures 52 units. 8 times 7 is 56, 56 minus 4 is also 52. We know those were opposite sides, so they were supposed to be equal, and because we got 52 on both, we knew that it worked. If we plugged 7 for B in here, we have 9 times 7, which is 63, plus 2 is 65 degrees, so that means angle Z is 65 degrees. 18 times 7 is 126. 126 minus 11 is 115. So notice these were not supposed to be equal. Those were consecutive angles, which means they were supposed to add to 180. And 115 plus 65 definitely does add to 180 degrees. So we know we did it correctly. We kind of skipped over the review problems in class. This would have been the way you would have set that up, and then cross multiplied and found that x would have been 24. All right, we're moving on to proving that we have parallelograms. Okay, again, we kind of skipped the warm-up, but the slope is 5 if you want to go back and do that problem. The next part of this was proving whether or not we had parallelograms. The thing is you have to know one of those properties is true in order to prove that it's a parallelogram. Even though this looks a whole lot like a parallelogram, the angles could be off by 1/10 of a degree. The side lengths could be off by 1/10 of an inch. So we can't go by just looks. We have to actually prove it. And so we have to prove one of those properties. And we only need one. We don't have to prove all 6. Okay, so by definition, that first property was opposite sides being parallel. So if we're given that information, we can conclude that it's a parallelogram because of that property. So here we're given that our opposite sides, ST and OP, are parallel, TO and SP are parallel, so we know it's a parallelogram. In the next one, we're given that opposite sides are congruent, that CD and FE are congruent, that's why they have those dashes, and that CF and DE are congruent, that's why they have 2 dashes, and so we know it's a parallelogram because of that property. Sorry, I didn't mean to knock that. Okay, next, we know some pieces of the parallelogram are congruent. We know that JT, which is part of that diagonal, is congruent to TL, and then KT and TM are congruent. Okay, so since we know that these pieces are congruent, that must mean that T is halfway along that diagonal, which means it's the midpoint. Well, it must also be the midpoint of KM because it has equal parts on both sides of T on that diagonal. So because of that, because we now know it's the midpoint, we know the diagonals have bisected each other. They've cut each other in half. And so that's how we know it's a parallelogram, is based on that property that diagonals bisect one another. Next, this one's kind of a combination of properties. We have where one set of sides is parallel, and then that same set of sides is also congruent. So here we have the LE and AK are congruent and parallel. That's going to also mean it's a parallelogram. Now, I have this trapezoid here to show you an example of why it has to be the same pair of sides. So here we have one set of sides that are parallel and one set of sides that are congruent, but it's definitely not a parallelogram. Excuse me. So it has to be the same pair in order to prove it's a parallelogram. Otherwise, you can only prove it's a trapezoid. The next property is where opposite angles are congruent. So if we know that information, we know it's a parallelogram. Okay, that last property that we would prove would be the angles being supplementary, and that has to be the consecutive angles. Again, this is one where it has to be supplementary to both of its consecutive pairs. So if we had, say, this trapezoid where we have two right angles, well, these are definitely supplementary and they're definitely consecutive, but it's not a parallelogram because we don't have both sets that are consecutive and supplementary. So an angle is supplementary to both of its consecutive angles would prove that it's a parallelogram. Excuse me, guys. Being sick threw me for a loop. In example 1, we're asked to prove that it's a parallelogram. We are going to do that by proving one of those properties. We have here that we're going to prove it's a parallelogram by showing opposite sides are going to be congruent. Excuse me, had to take a drink. We have expressions in the picture that show opposite sides, so those have to be shown congruent. So it gave me values of A and B that I could plug in. Excuse me. And make sure that those are equal. So I plugged in A equals 3 to both of the expressions that have A in them, because those are a set of opposite sides. And when we plug 3 in to both sides, we find that we have 34 equal to 34, which means that those sides are congruent. Here we have the same thing for B equals 9. B plugs in here and here, so I find that we have 51 equal to 51, which means KL and JM are also equal. Now then we can conclude that we have a parallelogram since opposite sides were congruent. The next example is asking us to determine if it has to be a parallelogram. Notice it gives us angles here. We know angles in a quadrilateral have to add to 360. We were missing this angle initially, so we had to solve for it by adding up our three givens. That equaled 287, and then subtracting that total from 360 gave us that missing angle of 73 degrees. Now, because we can now see that opposite angles are congruent, or we also know that 73 plus 107 is 180, and so we also have all of our pairs of consecutive angles that are congruent, consecutive angles that are supplementary. So we know that it has to be a parallelogram. And notice that's why I put 2 reasons on here, is because we could have shown either one of those and still proven that it was a parallelogram. But remember, you only need one. Example 3 was kind of an extension problem, and because in geometry we really don't solve systems that often, I kind of skipped over this one in class. This would have been the system of equations that you set up and then solve. And I'm not going to go through and solve this one in class because I won't ask a question like this in geometry. You'll do more of that when you were in Algebra 1 and then a little bit more in Algebra 2. So the way we're going to prove that it's a parallelogram is we use those properties. So that's the basis for the parallelogram, is those 6 properties. Now, next we had special parallelograms. So the 3 that we're going to be looking at is rectangles, rhombi, and squares. The first one was a rectangle, and a rectangle is a parallelogram, which, why I circled this is to make the point that those first 6 properties all apply. Like the opposite sides are going to be congruent, opposite angles are going to be congruent, diagonals are going to bisect one another, consecutive angles are going to be supplementary. So all those same 6 properties that we just dealt with for parallelograms apply to rectangles. Now, because it's a rectangle, we also can conclude, because of the definition, that all my angles are 90 degrees. So that's why I have here all of those angles are equal to 90 because of the definition. Now, next we have a rhombus. Now, I'm going to modify this definition a little bit because not only is it a quadrilateral, but it is a parallelogram, which is more specific because it means that those 6 properties that we've been dealing with apply. So a rhombus is really a parallelogram, but with 4 congruent sides. So because we know that this is a rhombus, we know that we have equal sides. Now, there are certain types of rhombi that are also squares, because a square is a parallelogram. I'm going to again modify this definition to say parallelogram with 4 right angles and 4 congruent sides. So you might have noticed that I kind of sectioned some pieces off from this definition. The 4 right angles part means that it's a rectangle because that was the definition of a rectangle. And 4 congruent sides means that it's also a rhombus. So because a square has that definition, that it has those properties, we can also say a square is a rhombus. A square is a rectangle. So any square is also a rectangle. The converse of that is not always true. Like, not all rectangles are squares. Not all rhombi are squares. Not all parallelograms are squares. But the statement saying all squares are those parallelograms, rectangles, and rhombus is a true statement. So every property that we've talked about so far is going to apply to a square because it's all of those things. Now, we analyzed some statements in class, answering with always, sometimes, or never. A square is always a parallelogram. There's not an example of a square that's not a parallelogram. A rectangle is always a parallelogram as well. It has all of those properties all the time. A parallelogram is sometimes a rhombus. Notice how this is kind of the reverse of how they were asking the question on A and B. A rhombus is always a parallelogram, but a parallelogram is only sometimes a rhombus. Because I can come up with excuse me, a parallelogram that is a rhombus, but I can also come up with a parallelogram that's just a parallelogram. It's not necessarily a rhombus. Now, this last one can cause some confusion. A rectangle is sometimes a rhombus. Now, a rectangle has 4 right angles. And when it's a rhombus, it has 4 congruent sides. Well, a rectangle that's a rhombus is a square. So when that rectangle has 4 congruent sides, it's a rhombus, which also means it's a square. Now, we have some additional properties that we're going to add to this. A parallelogram that's a rectangle has an additional property on its diagonals. The diagonals in a rectangle are equal. So here we have SO and TP. They're going to have equal measure. So that's going to help us solve some problems like example 2, where if we're given that it's a rectangle and we have a measure of a side or of a length in the rectangle and the measure of one of the diagonals, we can find x. So it gave me LP is 3x plus 7 and one of the diagonals is 26. Well, because rectangles have congruent diagonals, we know that both diagonals have to be the same measure. So if MK is 26, JL has to be 26. But because rectangles are parallelograms, we also know that parallelogram property applies that says diagonals bisect each other. So if they bisect each other, they cut each other in half. So we have 13 and 13, 13 and 13, which now means that that piece, LP, is equal to 13 units. So I know that expression, 3x plus 7, is equal to 13. And then from here, it's just a 2-step equation to solve for x. You can subtract 7 and then divide by 3 to get that x is equal to 2. Now, next we have some rhombus properties. The diagonals in a rhombus are perpendicular, which means they make right angles. So here, if we know that this is a rhombus, we can conclude that AD and CR are perpendicular. That's this statement means right here. And we have a 90-degree angle right there. But that doesn't mean that that's the only right angle. We actually have a right angle here, a right angle here, and a right angle here as well. So we actually have 4 right triangles that we've created. The next one is, sorry, that was my puppy in the background, that diagonals in a rhombus are angle bisectors. What that means, again, is bisect is to cut in half. So an angle bisector is to cut angles in half. So SL, because this is a rhombus, cuts angle S and angle L into 2 equal parts. And because we know it's a parallelogram, we know that those are the same equal parts on either side because opposite angles are congruent. And the same goes for angles R and T, that 3 and 4 are going to be congruent and 7 and 8 are going to be congruent. And then they're also congruent to each other. Now, in this next example, we're actually using that property. If we're given that angle 1 is 33, and we know this is a rhombus, we know that angle 1 and angle 11 have to be congruent because that angle has been bisected by that diagonal. And we also know opposite angles are congruent, so we know that those are also 33. And then we know that the diagonals are perpendicular, so we know we have those right angles on angles 3, 5, 8, and 10. Then we have a triangle here that we've created, and we know angles in a triangle add to 180. So 33 plus 90 gives us 123. Subtract that from 180 and we get that 57 degrees. But because those angles are bisected, we know that 2 and 4 are congruent, and their opposite pairs are also 57 as well. In example 4, we know the measure of angle 1 is 90 here because the diagonals are perpendicular, so they make a right angle. We know the measure of angle 2 has to be 45 because the corners are bisected by the diagonals. We know that ML is equal to 8 because all sides of a square, since we're given it was a square, are congruent. We were given that KL is 8, so all the sides are 8. And this piece of the diagonal here was 4 root 2. Because the diagonals bisect each other, we know the other piece is 4 root 2. Then we just add those together to get JL, which is 8 root 2. Now this chart right here helps us to see what properties apply to which shapes. They actually forgot one, so we added the diagonals are congruent to that last one, and that's a rectangle property and a square property. Now this just, notice those first 6 apply to all of these. Those first 6 properties are the parallelogram properties, and all of these shapes were parallelograms. Notice that square has everything checked, which means that it is also a rhombus, it's also a rectangle, it's also a parallelogram. As we look at example 5, we're just identifying what type of figure that is. We don't know that we have right angles right here, so we can't say that it's a square, even though it kind of looks like it should be. So we can just identify it as a rhombus, because we can't prove those right angles. Now we do have a right angle here in the center of this one, which means the diagonals are perpendicular. If you look at your little chart here, diagonals are perpendicular in a rhombus and a square. So because we know the sides here are congruent and the diagonals are perpendicular, we know that it has to be a rhombus. Now here we know that the diagonals are congruent. That's either a rectangle property or a square property. Because we don't know that the sides are all congruent, we have to conclude that it's just a rectangle. All right, moving on to trapezoids. We have some definitions to go over first. A trapezoid is a quadrilateral with at least one pair of parallel sides, and each of the parallel sides is called a base. So AX would be a base here and YZ would be at the other base. Because we are given that we have that set of parallel sides, we know it's a trapezoid. Also a property in trapezoids is that the non-consecutive base angles are going to be supplementary. So the angles on the legs are going to be 180. Here in this slide, we're just describing the pieces of the trapezoid. We have our base angles. They are on the same base. Remember, the parallel sides are the ones that are the bases, and then the other two sides that are not parallel are called legs. So base angles B and C come from the same base, and then base angles A and D come from the same base. And I also added in here angle A plus angle B will be 180, and C plus D will be 180. And that's for the same reason as the consecutive angles were in parallelograms. These are parallel, and these create a set of same side interior angles. All right, now this next theorem is probably the most important one for trapezoids. It has to do with the midsegment. Excuse me. A midsegment connects the midpoints of the legs. So we have the midpoint of this leg here, which means those two pieces are equal. So we concluded that. And then we have the midpoint over here, which means those are equal. So I concluded that here. Another property of a midsegment is that it's parallel to both the bases. So XY is parallel to both AB and DC. We could prove that by doing corresponding angles and also same side interior angles. We could prove it. I won't go through the big long proof with you guys. There's a formula to find the length of the midsegment. The formula is kind of like doing midpoint. When we average the two values together and we find the middle, that's exactly what we're doing here. We're averaging the two base lengths and then dividing it in half. So looking at these examples over here, I add up the two bases. So this is base 1, this is base 2. So I have x plus 40 divided in half should give me that midsegment, which is 21. Now I want to solve for that first base. So what I have to do is first multiply by 2 to get that out of the denominator. X plus 40 equals 42. Then notice I can get rid of 40 on both sides and just be left with x equals 2. That means that this other base measures 2. Notice that 2 plus 40 is 42, and half of 42 is 21. Okay, let's solve part B here. Averaging the two bases, so 15 plus 24 divided in half should give me the midsegment that I'm solving for here. So 15 plus 24 is 39, and 39 divided by 2 is going to be 19.5. So 19.5 is my midsegments measure. Now notice this last one, I'm solving for that bottom base. I can still set it up as base 1 plus base 2 divided in half gives me that midsegment M. So 14 plus x, 14 base 1 plus base 2 divided by 2 equals 19. Now multiply by 2 on both sides to get rid of that in the denominator. So I'm left with 14 plus x equals 38. Then subtract 14. So x equals 24. Now Oops, it's down here. You might also notice the distance between each one. Notice that 14, 19, and 24 on the number line have a certain distance from each other. 14 to 19 is 5 units. 19 to 24, 5 units. Notice that's the same on both sides. Hence, it's the middle, the midpoint. So you can also think about solving it that way, more just logically. If you know that 14 is 5 units away from the middle, then you know the other one has to be 5 units away. Just like here, 40 was 19 units away from 21. So 19 units away from 21 is 2. Now this next one, we are given expressions instead of just numeric values for those lengths. But we can still set it up as base 1 plus base 2 divided by 2 equals that midsegment. And that's what we've done here. 3x plus 1 was that first base, 7x plus 1 was that second base, divided by 2 equals that midsegment 10. From here, I can simplify that numerator. So I have 10x, 3x plus 7x, negative 1 plus 1 is 0. So 10x over 2 equals 10. You could multiply by 2 here, or just go ahead and reduce the 10 over 2. 10 divided by 2, I'm going to come over here, is 5x equals 10. Then divide by 5, so x equals 2. Okay, well, if we were to plug 2 in for our lengths, we have 3 times 2, which is 6. 6 minus 1 is 5. So that's the length of that first base. 7 times 2 is 14. 14 plus 1 is 15. So that second base is 15. Notice halfway between 5 and 15 is 10 units. Next we have an isosceles trapezoid. An isosceles trapezoid is where the two legs, the ones that are not parallel, okay, so the ones that are parallel are MP and ON here. Those would be my bases. Even though it's turned differently, base does not mean bottom here. In a trapezoid, base means the ones that are parallel. And so the ones that are not parallel are those legs, and in an isosceles trapezoid, those are congruent. So if I know I have a set of parallel sides and a set of sides that are congruent, that are my not parallel ones, then we can prove it's an isosceles trapezoid. Okay, next we have a problem where I want to prove something about the isosceles trapezoid. If I know we have an isosceles trapezoid, I know the base angles are equal. So if those segments are congruent, I know that angle F and angle E are congruent, and angle C and angle D are congruent. And those are my parallel sides here. So in example 3, I was given that angle T is 55. So instead of opposite angles being congruent here, it's where the base angles are congruent. It says that it's an isosceles trapezoid, so we know those two pieces are congruent. I know my two non-consecutive base angles are supplementary, so 180 minus 55 is 125. My base angles are congruent, so I know angle I is 55 and angle X is 125. Also, in an isosceles trapezoid, we have that the diagonals are congruent. So if I know one piece here, I know the other piece here. If I know that JL is 30, then I would know MK is also 30. We kind of skipped over example 4. And then lastly, the property of kites. We have what are called vertex angles in kites. The vertex angles are usually it's the long diagonals vertices. And then in a kite, one set of opposite angles are congruent. It's the ones that are the non-vertex angles. So angles B and D here are congruent. Diagonals are perpendicular, which means they make a right angle. So we have four right triangles in the kite. And then one diagonal bisects the other diagonal. So you can see here, if it bisects it, it's supposed to cut it in half. AC is not the one that's bisected. BD is the one that's bisected. So we have BY, those segments here, and YD that are congruent. Now, the quadrilaterals chart on the next slide, we're actually going to do a different version of this in class on Monday, so you don't have to worry about this or the review problem, which is just simplifying an expression. So those are the notes for the quadrilateral properties. From that, you should be able to complete the assignment. The assignment is just using the properties that we've already gone over. So in that, try and look for those properties, like those 6 parallelogram properties, finding opposite angles, finding opposite sides,